Hello, this video is an introduction to Snell's law, or the idea of refraction. So in order to give you a start, I'm going to show you a quick, interesting magic trick. Call it a magic trick, the reappearing penny. And so watch this video real quick and then we'll talk about it. For this demonstration, all I'm going to use is 2 cups, 1 full of water, and a simple penny. I'm going to put the penny in the empty cup, and it's going to bounce right out again. Try again. Okay, and I'm going to put the penny towards me, and then I'm going to move the camera so the penny is just out of sight. So I'm going to move it till the penny is just out of sight. Right there. I'm going to do it again. So we're moving till the penny is just out of sight. There we go. Now we can't see the penny, but what happens when I slowly pour in the water? And slowly, so I don't move the penny itself. As I slowly pour in the water and we get more and more water into the cup, we actually can see the penny. So how does that work? What's going on? The penny was not in our line of sight, but now with water we can see part of the penny. This is refraction. All right. How did we get to see the penny when it hadn't been visible before? We think about the cup, and the penny was here, and we put our eye right where we couldn't see the penny anymore. So here's our eye, because it was blocked. So right where that light ray went, nope, not doing it. Oh, what a mess. But then when we added water, suddenly we could see the penny, which meant that there was a light ray going from the penny into our eye. But we know that a direct line was blocked by the edge of the cup. Well, that means something weird happened, and this is the idea of refraction. The light had to bend somehow. We know light travels in straight lines, but something weird happens when light switches from one material to another, or one medium to another medium. So what happens is there's a light ray that goes up, and then it bends when it leaves the water so that it goes into our eye. There is a bending of the light when it goes from water to air. And that is refraction. So we are going to have a couple definitions. Ooh, let's say this is my air-water surface. So we've got air here and water here. This light ray, in order to see it, it had to start here. So I'm going to have a light ray that comes from the water, and then it bent in this direction. We are going to define the perpendicular to the surface as our normal. So that is the normal line. And if you think back to College Physics 1, we used the idea of a normal with a normal force. The normal force was always perpendicular to the surface. Normal is a kind of mathematical way of saying perpendicular. So, normal force, I caught myself, normal line, the normal line is perpendicular to that surface. If we had a surface like a piece of glass, and we have a light ray coming in like that, then the normal perpendicular to the surface. So if we had a little prism, triangular prism, our normal would look like that. Okay, so something happens going from water into air. It bent away from the normal. And this bending depends on 2 different things. See if you can come up with what would affect the bending of light when it changes from one medium to another one. Can you think about what variables would change how much it bends? Yeah, thought about it? Thought about it? Okay. Well, it turns out there's 2 things, as I said. One is the 2 different materials. If this was air into air, it wouldn't bend at all. And so you have to have 2 different materials. And what the materials are made of does make a difference. If I had air here and glass here, it would bend a different amount than air to water. So the material is one thing. The other thing is the incoming angle. And so we can see this with a quick simulation that I will throw into this, and you can see how the angle makes a difference. Okay, so refraction happens because light changes speed when it changes media. When we go from water to air, it bent this way. Now let's think about the process of light moving through materials. Do you think that light moves faster through air or faster through water? Just make your best guess. You think it moves faster through air or water? Most people think it moves faster through air, and that is correct. So the light moves faster here, slower in water. This idea of how fast light moves is called the index of refraction. And it is given the symbol n, lowercase n, no units. You're going to like that because no units. And the index of refraction is a measure of how the optical density is often a way I talk about it. It's optical density. Is light going through it quickly, or is light slowed down a lot? Air is not very optically dense. It has a small index of refraction. Water is more optically dense. It's harder to travel for light to travel through. Glass is even higher optical density. And so the index of refraction, N, is this idea of how hard is it for light to travel in this material. And it's actually just a ratio. It's a proportion of the speed of light compared to the speed of light, oh, I should be careful, the speed of light in a vacuum to the speed of light in that material. So it's just a ratio. They're both speeds, which is why we end up with no units. And the numbers that we will typically see, 1.0 is the smallest. That is, if we're in a vacuum, then it's C over C, 1.0. The biggest we're going to deal with is about 2.4, but it does go up to 4.0 even. And so you can go up pretty high. But mostly we're going to have the range of 1 to 2.4. Some common indices of refraction. The index of refraction of air. Well, light does travel through air very well. It's almost the same as vacuum. You have to go a couple more decimals out in order to get it, to see that it's a little more than 1.0. Water, another common material. The index of refraction of water is 1.33, 4/3. And then glass is another one we typically talk about, and that is about 1.5. Because there's different types of glass, you can't say it, every piece of glass has the same index of refraction, but they tend to be about 1.5. And again, the biggest ones we'll be dealing with are a little above 2. I think diamond is 2.4, and that's probably the biggest one we'll use. So we have this idea now of index of refraction, and then we know that light is bending. So this was a small index of refraction, and this had a bigger index of refraction. So if we are going from a big index of refraction to a small index of refraction, we can say that the light is going to bend which way? Well, it bent away from the normal. Light bends away from normal. And then you can probably guess if we go the other way. Let's see. If we go from air, now I'm going to go this way, into water, these two will match up exactly the same. And so from little to big, from small n, small index to big index, light bends towards the normal. Oh, how do I spell towards? There we go. Light bends towards the normal. So these are the two kind of rules about how light bends when it encounters a new material. Depends entirely on the relative index of refraction of each of the materials. And so if we're going into something more dense, it bends towards the normal. If we're going something into less dense, it bends away. And we can see that in the simulation. So with this is all kind of the concepts. We can actually figure out mathematically how much this light bends. And again, it depends on two things. It depends on the materials and it depends on the angle. So when we're dealing with the math piece of it, the most important part of this refraction idea is where you measure your angles. And every single time we're dealing with refraction, you are going to measure the angle to the normal. Angle to the normal. So it's this one and this one. I don't care what the angle is from the surface. We don't use that. The reason we draw the normal is so we can figure out the angle to it. So if you do not have a normal line on your picture, you probably will not be able to get the correct angle. So angle is always measured to the normal, not to the surface. Measured to the normal. And the mathematical equation for figuring out how light bends is called Snell's law. I'm going to see if I can get a less squeaky marker. That's a lower note, at least. It's called Snell's law. And I love Snell's law because it's symmetric. It is n sine theta equals n sine theta, where we have index of refraction of material number 1 times the sine of the angle in material number 1, and that is equal to, same thing in material number 2, times the sine of the angle in material number 2. And so when we do Snell's law, we can just use this neat little symmetric equation to help us figure out where light is going to end up bending to. And we can do some quick calculations, give it a try. Suppose I've got, oh, I just erased what I wanted. That's okay. Suppose I'm going from, let's do air into water. And let's see if we can actually show that the light will bend. Okay, air into water means we're bending into, we're going into a more dense material, which means we should bend, it was right here, should bend towards the normal. If we have an angle in air of, there we go. Let's get my normal line. Okay, let's see, air into water. Let's say we have an incoming angle in air of 60 degrees. And again, that is to the normal. So this is my 60. Well, my angle in water, should note what our materials are there. I know it should bend towards the normal. What is this angle? So I have angle of air is 60 degrees. I want to know what the angle in water is. Index of refraction is the other piece I need. For air, it's 1.0. Index of refraction of water is 1.33. So let's pop it in here. I'm going to start on this side. We're starting in air. Over here, we're going to be in water. So n sine theta. So index of refraction, well, I guess I can just start by throwing in numbers, can't I? Oh, you're still wet. So 1.0 is the index of refraction of air, times the sine of the angle in air, 60, equals index of refraction of water, 1.33, times the sine of the angle in water. All right, there's only one unknown. It is solvable. But if you've been away from your math for a little bit, you might have trouble remembering how to get an angle out. So if we're to solve this for the angle in water, what we're going to do first, let's see. Well, I'm just going to ignore the 1.0 in front here, right? That's the same as this, so let's get rid of that. That's a little bit easier to see. I want this, okay, let's get rid of that. So I'm going to have the sine of 60 over 1.33 equals the sine of the angle in water. To get the angle out, you don't divide by the sine, because that's just going to be sine of angle over sine of angle. That'll just give you 1. So how do you get rid of a sine? It's the same idea as if you have an x squared and you want to get x. Well, what do? In order to get rid of a square, you do the square root. They're kind of the inverses of each other. There's the key word, inverse. So what I'm going to do is the inverse sine of both sides. Sine 60 over 1.33 equals the angle in water. And I think what I'll do is I'll actually show that middle step. Sine, okay, so inverse sine on both sides. And then on this side it was still sine theta water. That cancels that. Whoop, I don't know if this is visible. So the angle in water is going to be the inverse sine of, big parentheses, sine of 60 over 1.33. In your calculator, don't forget to put an extra parentheses here, because otherwise you'll do the sine of 60 over 1.33. No, we want the sine of 60. Figure that out, then the 1.33. All right, go ahead and do it in your calculator. And what you should get, now we were guessing it was going to be towards the normal, which means less than 60. And if you calculate it, what do you get? What do you get? 40.6 degrees. So it bent almost 20 whole degrees. That's a lot. And that is our answer. Oops, we'll include the degrees sign. So that is just your basic Snell's law. It's the idea of refraction. When light moves from one material into a different material, that light gets slowed down or sped up, and that means the light ray actually gets bent, and we can figure out how much that bending is by using Snell's law, which is this wonderful little symmetric equation. I really like it. Symmetric, it's just like whoop, whoop, whoop. Doesn't matter which way you go. If you were to do water into air, it would be the exact same calculation. So if I started with water, so if I started with a ray in water at 40.6, it would go out at 60 degrees. That's what this symmetry here means. So it's a fun one. I like doing it. All right, well, there's your introduction to Snell's law. Good job for watching.